Today's lecture is going to be about hidden Markov models, and the main focus will be to learn how to predict a sequence of labels, or in other words, also assign a probability to a sequence of labels, or what we call sequence labeling in general. So, but before we start with today's topic, we'll just, as usual, do a quick recap of last week. So. The things that we have learned last week, first we introduced basic probability theory concepts, or not introduced really, but reviewed. So basic axioms, the difference between a joint probability, conditional probability, the concept of independence. So when two events are independent, what does that mean, and what does it entail into when we compute conditional probability or joint probability, and the Bayes theorem. And what we tried to learn last week is how to predict the next element in a sequence. So that was the language models. So given the first few words or 3 words in a sentence, what comes next? And also another aspect of that is assigning a probability to a full sequence. What's the probability of a sentence in English? So we said that previous contexts can help predict the next element of a sequence, and for example, words in a sentence. Of course, as we looked closer at this, we realized that accounting for the full context, the full history, could be problematic, not least because language is very creative. So there are certainly new sentences that will be said that we are sure these sentences have never been said before. They are fully grammatical sentences. They make sense, but still we will not be able to manage for to account for all possible sequences or sentences in language. So we relied on this Markov assumption, which in general terms it means that we can predict the future state of some system based on the recent history. We don't need to look at the full history. And we applied that to our models, and we said we can predict the next element based on the last n-1 elements. We don't need to look at the full history. And that led us to define n-gram models, bigram, trigram, etc. And yeah, so an n-gram model would predict the nth word conditioned on the n-1 previous words. And in order to learn these the conditional probabilities and these estimations, we used something called the maximum likelihood estimation, which uses relative frequencies to approximate the conditional probabilities. So in a bigram setup, a relative frequency means we look up, for example, say we have wi minus 1 and wi. We count how many times we see wi minus 1 followed by wi, and we normalize that by number of times we see wi minus 1. So the context. And of course, this Markov assumption didn't mean that we actually solved the problem of unseen events, or in this case, unseen bigrams or trigrams. So we had to rely on smoothing techniques, which in general terms are techniques that move some of the probability mass from frequent events to infrequent events. So in the specific technique that we gave is the add-1 smoothing, or the Laplace smoothing, where we assumed that no event will have a count of 0, but at least, so any event or any bigram, and when we talk about language models, will have occurred at least once. So we will add 1 to all the counts. So this would help us get rid of zero probabilities and make our system more sort of intuitive. So this is a very quick recap of what we did last week. Do you have any questions on that? Okay, so again, this is something we have seen last week. So for the rest of the semester, we want to learn to predict these different types of structures, or linguistic structures, or assign probabilities to them. So what we did last week was the first type, where we assigned probability to a sentence, to a string. So we wanted to define which one which of these two sentences is the more likely. And the more likely means has higher probability. So she studies morphosyntax, she studies morphosyntax. We use a language model to assign a probability to these two sentences. Well, so this is done. What we want to do today is the second type of prediction, in a sense. So we want to assign a sequence of labels to a given sequence of words. So in general terms. So in this example here, we have a sentence like flies like flowers. So last week we had time flies like an arrow, if you remember. If we look at flies like flowers, there are at least two possible sequences of labels that we can assign to this, and they differ because the word flies could be a noun in plural, so noun in plural in English, or the third person singular verb. So he flies, or it flies, he reads, it reads, in contrast to I read. So we add this S to mark that this is a verb in the third singular person form. So and of course this has also implications on what kind of label we can assign to like, whether it's a verb or a particle. So these are two likely interpretations or sequences that we can assign, and we want to determine which one is the more likely, which one has the higher probability. So our example, or sort of our framework for today, is going to be part of speech tagging. So assigning parts of speech to words. So we'll start with a very quick and brief introduction to what we mean by parts of speech tagging, so that just you're all familiar with the concept, because in assignment 3A, you're going to be working with parts of speech tagging. So you probably already know what we mean by parts of speech tagging, but have heard different names for it. So parts of speech tags could be also referred to as lexical categories, word classes, morphological classes, etc. And there are many ways to define parts of speech tags. So you can define them based on semantics, but you can also define them based on syntax and morphology. So in terms of semantics, parts of speech tags could be defined. So something like noun, for example, could be defined as the words that name things, or name places, or name people. So nouns in general, from a point of view of semantics, have some kind of semantic coherence. So sort of they tend to denote a person, a thing, a place, an institution, etc. So that's from the semantics point of view. But also nouns, verbs, etc., these different types of word classes, they exhibit similar behaviors in terms of syntax and morphology. So what do we mean by that? So for example, nouns tend to follow determiners. So this is a syntactic property of nouns. So there's a distributional, if you want, distributional property of nouns that says usually you will see nouns following a determiner like the. But also sometimes there will be an adjective between the noun, and so the boy, the nice boy, for example. So there is an adjective here. But there is still a general characteristics that can define nouns, and you can also take this definition further by adding the morphology side of it, which is nouns takes an S when they are in plural form, in general. That's the general case in English, of course. There are exceptions, but generally, whenever we want to transform a noun from singular to plural, we add an S. So S, this is the plural marker in English. So as you can see, and you can say that on verbs, etc. So as you can see, there are syntactic and morphological properties that we can observe from data. We can see it. So semantics, we cannot immediately see it from just looking at a corpus, a large body of text. But these morphological properties are observable from the text. So we're going to take this definition that is based on morphology and syntax to be our way of defining the different types or of word classes, of the different types of parts of speech tags. And we distinguish between two super types of parts of speech. So one we call the open class, and the other we call the closed class. The open class includes nouns, verbs, adjectives, adverbs, and it's called open because it's relatively easy to add new members to this class of words. So you can add. So maybe 10 years ago, 15 years ago, there was no word such as Google, for example. Now you can use it in the verb form, also as a noun. Also the same could be said on Twitter, tweet, to tweet. So a tweet is a noun, to tweet is a verb, etc. So as you can see, as with time, it's relatively easy to add new concepts, new names, nouns, verbs, adjectives, adverbs, etc. Now, if you contrast that to the closed class, so the closed class is this class of types of words that don't that have a static membership, meaning that pronouns, for example, which belongs to the closed class supertype of words, pronouns are relatively static now. You don't see new pronouns added every decade. Or the same can be said about determiners or prepositions. So this is the difference. One is more static, one is more fluid, changing over time. And closed class words could be seen also as function words. So words that are sort of not contributing a lot to the meaning, but rather to the construction of the full sentence and sort of making it more grammatical. And also stop words that we have talked about before tend to be part of closed class word types. So if you look closer at these different sort of word classes in sort of in a very general way. So nouns, for example, you know, nouns such as dog, Oslo, people, etc. So these are nouns. And they are, as I said, generally defined from a semantics point of view as these words that are naming people or places, things. But this concept, nouns, can be further refined to make distinctions between the different types of nouns. So we have proper nouns and common nouns. So proper nouns are nouns that are naming institutions, people, cities, whereas common nouns are more like for things. You can also distinguish between count noun and mass nouns, or countable and uncountable nouns. So a countable noun is a noun that can be modified by a numeral. You can define it this way. So one phone, two phones, three phones, etc. Whereas uncountable or mass noun is something like water or information. You can't say two waters. This is not grammatical. And also you can distinguish between them is that one of them can be inflects in the plural form, the other doesn't. So mass nouns they don't inflect in the plural form. Yeah. You could say that, yes, but it's still a so money is a clearer example maybe. Exactly. But normally you would say 2 glasses of water, right? Or if you think of money, for example, also two monies. What does that mean? Money is uncountable in the sense that it's a mass noun, or information. So people would say informations, but it's a mass noun. It shouldn't be countable. You say 2 pieces of information, but really this isn't. Of course, there are fuzzy boundaries, and language would change over time. So I think at one point homework was not countable, and then it becomes homeworks over time. So I'm not. It's as you said, it's fuzzy. I mean, and language changes. I mean, language is use also. This is one of the definitions. The way you use language is actually how the language will evolve. So semantic drifts and the meanings of words. So some words used to have different meanings, but because people started using them in different contexts, they evolve so they get a different meaning over time. And that's what we call, for example, semantic drift. When a word over time is used over and over again in a different context, then it becomes an acceptable meaning of this word. But I agree, there are fuzzy boundaries, of course. And yeah, just yeah. Also, further distinctions could be made on whether a noun is a plural or a singular, feminine, masculine, etc. And the level of distinction you make between these different, so whether you say I only care about nouns, or I want to distinguish between proper nouns and common nouns, or between countable or uncountable nouns, completely depends on your application, and also on the design of the corpora or the sort of the data set you're using. So as we will see later on, we're really not so much concerned on how fine-grained or coarse-grained these distinctions are, but just that you know they exist, and different annotation or linguistic frameworks in computational linguistics will make these distinctions. Others will see that this is not helpful for our own application. We don't care whether this noun is a proper noun or a common noun. All we care about is it's a noun. Verbs. So nouns are naming things, places, institutions, etc. Verbs are describing actions and activity. So fly, rained, having, seen, etc. And again, also here we can make further distinctions. So we have transitive, intransitive, detransitive verbs. So verbs that transitive are the verbs that select for an object. Intransitive, they don't require an object. Detransitive, they require a direct object, indirect object, etc. And also we can distinguish between them based on the tense, etc., etc. Again, also we have another type of open class words, which is adjectives. Adjectives are used as modifiers, mainly to nouns, but also they can modify another adjectives, and they describe a quality or a characteristic of some sort. And there again, you can say it's enough for me to know whether this word is an adjective or not, but you can also take it a bit further and say we want to distinguish between superlative and comparative form, for example, so faster and fastest, or whether we want to distinguish between a predicative and attributive, so where the adjective actually occurs. So an attributive adjective is, so in the case of the unhappy cat, so here the adjective is attributive, the cat is unhappy, this is a predictive adjective. Again, really that's not so important in our work today. Adverbs, more like adjectives also, but they can modify verbs and also adjectives. And again, also you can make several distinctions between the different types of adverbs. So these are the three main sort of types of open word classes, and they tend to also have further fine-grained distinctions depending on the framework that we're going to work with, or the data set, or the closed class words are, as I said, these small this group of words that has a static membership, and their main function really is to make up make it possible for us to put different pieces together in language. So we use determiners, for example, in front of nouns, or to denote whether a noun is a definitive or indefinitive, etc. We use conjunctions like and to make more complex. So put two phrases together to make a complex linguistic construction. Pronouns are used as shorthands for nouns. So you say a noun and then you start using a pronoun to refer to that noun, etc. Yeah, I don't think we need to spend more time on sort of these definitions. It's just good to sort of get a very sort of high level understanding of what we mean by these different types of words. So as I said, today we're going to work with sequence labeling, and the particular problem we're going to address is part of speech tagging. And part of speech tagging is the automatic assignment of part of speech to word sequences. So we're given a sentence, and for each word within the sentence, we're going to assign a part of speech. But we handle this problem, or we work with this problem as a sequence labeling problem. We don't just look at each word in isolation, because if you remember, as I mentioned before, there are syntactic properties and distributional properties, in a sense, that also govern how we use these different types of part of speech. So again, a determiner is more likely to be preceding a noun than a verb, for example. So it's a sequence labeling problem. Why is it of concern to us? It's actually a non-trivial problem, mainly because words are ambiguous in terms of their parts of speech tag. So, you know, we have established this already, that language is very ambiguous, and there are many different levels of ambiguity. And one of these levels is the lexical categories, or the parts of speech tags that a word can take. So a word like fly could be a verb, it could be a noun, right? So it could be fly the insect, fly, verb to fly. And if I say just fly, you don't know whether I'm referring to the verb or to the noun. But when I say I fly, you know that I'm talking about the verb now. Otherwise, yeah. I'm not a native speaker, so I really don't know whether it can be an. Yeah, I'm not a native speaker of English, so adverb. Adjective, you mean, or? Yeah, it might be. Yeah, it's possible. Yeah, it's possible. I mean, there are words that could take more than just the same exact word could have more than two types of parts of speech. If anyone knows, anyone is cooler than me knows this new. I don't know, but yeah, I mean, this is just adds to the point that it's actually ambiguous, right? So whether it can be an adjective or not, this is still an ambiguous word. And in order to resolve this ambiguity, what we need to do is to look at the context. So as I just said, if I just say fly, or if I just say book, for example, so because book could be the book that you read, it could also be the verb to reserve. So you book a flight, but you also read a book. So these words, without any context, are ambiguous. They could be the same orthography, the same exact word, could have different types of parts of speech, and we need the context to resolve this ambiguity. And this task of assigning parts of speech is useful as a pre-processing step for parsing, syntactic parsing, building syntactic structures for sentences, which we will be looking at starting from next week. But they can also be directly usable for applications such as text-to-speech systems. So these systems that given a text, it reads it out loud for you. So you find it nowadays on websites where there are many websites providing this. You're reading, you open an article and you can actually get the website to read it out loud for you. And here it's important to know when you do this, when you work with such systems, it's very important to know what is the part of speech of a given word, because a word like this one here depends on. I'm not going to pronounce this because if it's a noun, it's content, right? If we're referring to the noun, we say content. But if we are talking about the adjective that you are satisfied, we say content, right? So the pronunciation, the stress pattern, differs between whether this word is a noun or it's an adjective. So a system like Siri, for example, if it wants to read out a sentence for you, it's important to know where to put the stress. And in order to do that, you need to know what type of part of speech this word is. So Siri will not will say something like, cannot say, I hope you are content with the content I'm providing you. That doesn't make sense. I hope you are content with the content I'm providing you. You see the difference here? So this is a clear problem that needs to be solved, and one solution to this is assigning parts of speech to the words within a sentence. Now the difficulty and the usefulness of using parts of speech tagging depends on what we call the tag set, or the set of parts of speech that we take to describe the different word types. And as I said, there are many different tag sets. So different linguistic theories or different linguistic annotation frameworks will have different types of part of speech tags. What we will be working with is the tag set of the pen tree bank. So the pen tree bank is you can think of it as a data set. It's called tree bank because first of all it consists of text from the Wall Street Journal taken from the 80s I think or the early 90s. So lots of text that was manually annotated with syntactic analysis. So each sentence has a syntactic tree, which again which we'll look at next week. And also the leaves of these trees are part of speech tags. And the creators of this resource, of this tree bank, decided that they're going to need 45 types of parts of speech tags. And these types include nouns, but these nouns, for example, make the distinction. So NNS is a noun, the plural form. NN is a common noun in the singular form. And NP is a proper noun. JJ is an adjective. JJR is an adjective in the comparative form. JJS and an adjective in the superlative form. So you can see the full tag set on this link here. So actually, this should be okay. Sorry, there must be a different one. This is not it's not working anymore. This is a this link is broken. So I'll change it before I put the slides up. So anyway, so whether the problem is difficult or not, again, as I said, it depends on what type of distinctions we make. So do we make the distinction between a proper noun or a common noun, etc. And whether it's useful or not also depends on the application and these distinctions. There's also a tag set for Norwegian, but I'm not very familiar with it. So, but you can feel free to also investigate more on this link. So, as I said, we are interested in assigning probabilities to tag sequences or a sequence of part of speech tags to a given sentence. So a sentence like "flies like the wind." It's ambiguous, and both analyses here are actually likely, because the flies, the insects, could actually like the wind because for some reason, and also flies like the wind is like something times flies like the wind. So, but in the reality, when you work with language analysis and text processing, you will not see this part of speech tags, right? So all you see is just the words. And in this case, what we would say is that part of speech tags are this underlying skeleton of the sentence. It is unseen, so we don't see it, right? So it's something we have to provide, but it gives us clues on how the sentence should be interpreted. So the way we decide to assign these parts of speech tags will lead to different meanings of these two meanings of this sentence. And a situation like this, where you have a visible, observable sequence and invisible one or unseen one, that determines sort of, or that serves as the skeleton of the observable sequence. Situation like these, a hidden Markov model, the model that we're going to introduce, could be very useful. So from now on, we will refer to the set of these part of speech as the hidden state sequence. It's hidden because we don't know it. We want to find it. We know it's there. We know that for each of these words there is actually a part of speech, and we have the observation sequence, something that we see in the text, which is the sentence, the words. So the sequence of words is what we will refer to from now on as the observation sequence, and the sequence of the parts of speech is the hidden sequence. And these two parts make up a hidden Markov model. So the structure of a pairwise aligned two sequences, one is hidden and one is observable, is sort of a typical prototypical a problem to be solved with hidden Markov models. So the two important things to understand here is that we have two sequences. One is observable, one is hidden, and these two sequences are pairwise aligned. So for each word, there is a part of speech tag. So they will be always of the same length, and they are aligned. So if you remember this generator concept, or the generative story that we call it last lecture, where we tried to generate sentences, English sentences, using an n-gram model, we can do the same here with hidden Markov model. So we say that let's have a pseudo state denoting the start of a sequence. So this S here, and we ask our model what is the most likely part of speech tag, given that we know that we are at the start of the sentence. And our model will return, for example, here, determiner. DT is determiner, so it could be the. Now this part looks like a lot like a bigram model, right? So this is what we had before. Given the current word, what could be the next one? The second part, which is sort of here comes the relation to the words, is given that we have this part of speech tag, what's the most likely word? So given that we have a determiner, what is the most likely word that we can generate, in a sense? And to what we want to compute in the end is the joint probability of a sentence, or sorry, of a sequence. I didn't introduce. So S is the sequence, the hidden state sequence, and O is the observation sequence, is the words, in a sense. And we want this sort of model to generate a joint or to give a joint probability to a sequence, hidden state sequence, and an observation sequence. So we can move on by asking now that we have a determiner, what is the most likely part of speech tag to follow a determiner? It's going to be a noun, etc., etc. So this is the overall sort of picture of how you could imagine a hidden Markov model generating both the sequence and the hidden state sequence and the observation sequence. This is just to link this picture to the picture we introduced last week. But what really matters to us is the formal definition of a hidden Markov model. So in a hidden Markov model, as I said, you have an observation sequence, which is from 1 to n. If you think of part of speech tagging, this is our sentence. And what we want to compute is the joint probability of a hidden state sequence and an observation sequence. And this could be computed using the chain rule that we introduced last week by multiplying the probability of Si given Si minus 1. This is an element within the hidden state sequence. So Si is an element of a hidden state sequence. So the conditional probability here is again very similar to what we introduced last week in the bigram language model, but now we're working with part of speech tags. And we multiply that by the probability of seeing an observation OI, this element OI, given that we have seen the state Si, the hidden state Si. And again, we introduce S0 and n plus 1 as the start and end symbol. So we call this term, the first term, the transition probability. The transition probability is modeling the probability of transitioning from one state to another. So state S minus 1 to state Si minus 1 to state Si. So we will refer to this part, to this term here, as the transition probability. And we will refer to this term here, the probability of OI given Si, as the emission probability, which models the probability that a given state emits a particular observation. So given a state Si, what is the probability of an observation OI? Again, as I said, these two sequences are aligned. So for each element within the hidden state sequence, there is an element in sort of a corresponding element in the observation state sequence. And so this would be the basic or the starting point. So we're going to improve this definition. So, but this is our starting point for defining how we compute the probability of a hidden state sequence and the joint probability of a hidden state sequence and an observation sequence. So, in terms of part-of-speech tagging, again, this is the probability of a sentence, the joint probability of a sentence, and a corresponding sequence of part-of-speech tags. And we can use hidden Markov models to sort of to solve many different types of problems. It depends on how we define our problem. So the one that I just introduced, which is the joint probability of a hidden state sequence and observation sequence, given that we know both of them. So when we compute the joint probability, we assume that we know both of them, right? We know what is the observation sequence and what is the hidden state sequence. This is a very rare case in natural language processing. You wouldn't naturally or normally you wouldn't know both the observation sequence and the hidden state sequence, because as I was just saying, we actually don't know the part-of-speech tags. We want to generate them. We want to find them, find the best sequence. So this is this one here. Is really not common at all, not a common setup that you will have. Another common setup that you can use hidden Markov models with is to compute the probability of an observation sequence. Just that, regardless of the hidden state sequence. And this is something we know already. Do you know what is this? So to compute the probability of O, the observation sequence. Yeah, exactly. That's what we did last week. So we can actually use hidden Markov models as a language model to compute the probability of a sentence. But here it's more complex. Even though I'm saying we just want to compute the probability of O, the sequence O, we still need to account for all the possible scenarios of the different hidden sequences. We will look at this later on in the lecture and how we can actually use a hidden Markov model as a language model. The setup where we are going to use, which we are going to use with part-of-speech tagging, is this one here, where we are looking for a hidden state sequence S that maximizes the probability of S given O. So we want to look for the sequence of part-of-speech tags that maximizes the probability of S given O, where O is the sentence. Yeah. Then minimize the not S, but that would leave you with a set of more likely sequences, right? So, but because what you will get from here is just one sequence. So I'm looking for one sequence that maximizes P of S given O. Now, what you want is what you're proposing is to look for not S that minimizes P of not S given O. Yeah, I'm not sure, because that will give you the most unlikely, maybe, right? I have to think about this, but I'm not sure if that will work. I'll think about this in the break, or okay, but yeah, because I realize I'm a bit slow, and yeah. So this is the main formulation that we were, or sort of the first type of problems that we're going to look at. These transition and emission probabilities are probabilities that are we will learn from data. So it's a data-driven approach, so we can learn them from an annotated data set, and they are called the model parameters. So just like last week where we talked about model parameters being the conditional probabilities, here again the transition and the emission probabilities are the model parameters. Again, in our part of speech tagging problem, the observations are words, WI, and the states are part of speech tags. So WI is a word within the observation sequence, and TI is the tag number I, so tags. So as I just said, we will assume a supervised learning problem here. So we'll assume that we have a data set that consists of already annotated sentences with part of speech tags, and we'll use these. We'll use this data set to learn the transition probabilities. Again, as we did last week, we'll use the maximum likelihood estimations. So to compute the probability of tag TI given TI minus 1, we count how many times we see TI minus 1 followed by TI, and we normalize that by the context, or in this case, TI minus 1. So again, it's just counting, and this is exactly the same as we did last week. So go to, so in order to count the probability of 2 given go, we looked up how many times we see go to, and then normalized that by how many times we see go. And here we apply the same, but just for part of speech tags rather than words. The emission probabilities also computed the same way, maximum likelihood estimation. So we have a given word, WI. So what we want to compute is the probability of WI given TI. So the probability of a word WI having seen the tag TI, and this could be also again computed from our data set, where we see that each word has been annotated with a particular part of speech tag. So we count how many times this given word was tagged with the part of speech tag called TI, and then we normalize that by the number of times we see this particular type of part of speech tags and the full data set. So these are the basic computations that we need to do to learn the model parameters. Yeah, again, very quickly, this is when we start working with hidden Markov models, we will see the same problem as we have seen in language models. So probabilities are limited to values between 0 and 1, and multiplying probabilities means that you will likely end up running into a floating point underflow. So this is something we mentioned last week. So we move our work from the linear space to the logarithmic space, where multiplication could become or becomes a addition. So this is just a comment aside. And again, the same problems that we have seen in relation to sparsity, you will see them here again. So sometimes you will have 0 probabilities and you'll need to do smoothing, but again here smoothing would be done on the transition probabilities and the emission probabilities. So basically, since it's basically the same way of computation, you can apply smoothing in the same way here. Add one smoothing, for example. I'll introduce the problem maybe, or I should have finished this before the break. Okay, let's take a break now, but then come at 13 past exactly, so we have time to finish the lecture today, or what we're supposed to finish. Start again. So even though as I said, our main problem is part of speech tagging, we'll look now at a smaller sort of tiny problem, a toy example, so that we make sure that we understand and follow all the different steps. So our problem here is related to ice cream and global warming. So assume that you live now in the year 2700 or something like that, and you were assigned the task of studying global warming. And the weather records for all the years are available except for one area in the summer 2007, which is Baltimore. So we have missing information, but what we have is someone called Jason Eisner, who used to keep track of his ice cream eating habits. So he would, for each day, write how many ice creams he ate. And this daily record of ice cream consumption would help us somehow uncover the weather in the summer of 2007 in Baltimore, because we know there is a relation between the number of ice creams eaten per day in contrast to the weather. So if it's hot, so on hotter days, Jason was more likely to eat more ice creams, and on cold days, he was sort of eating less ice creams. So we will use the number of ice creams that Jason recorded for each day to uncover the weather forecast, or the weather measurement in that day and each day. And as you can see here, so the number of ice creams is the observation. So that's something that's, we have a sequence of days. For each day there is a number of ice creams. So that's our observation sequence, and the hidden sequence is the weather on that day. So this can be represented as a problem that we solve using hidden Markov models, and it makes sense to present weather, of course, as a sequence, because in order to predict the weather today, we partially rely on the weather yesterday. So the weather is not random. So it's a sequence. Today depends on yesterday, and tomorrow will depend on today. So the sequence of weather predictions is also it makes sense to have this problem as a sequence labeling problem. So we'll introduce a hidden Markov model, which has hidden states and observations. So we will limit our weather measurement to whether the day was hot or cold. It's very coarse-grained. So we have only two states, a hot day and a cold day. Plus two pseudo-states that we are familiar with now, the start symbol and the end symbol of a sequence. And the observations is 1, 2, 3. So what this means is that Jason wasn't, at most ate 3 ice creams per day. Sometimes he ate 2, and also sometimes he ate 1, but never less than 1 and never more than 3. So our sequence of observations will be drawn from 1, 2, 3. So there will be 1, 1, 1, 1, 2, 3, 3, 3, 3, 3, 2, 1, 3, etc., etc. So you can make the sequence yourself. So if we try to represent this, to represent our problem and assume some probabilities. I mean, it's a small problem. We can assume some probabilities to work out through the example. So the circles here are representing the states, the hidden states. So we have 4 states. 2 of them are pseudo-states, start state and end state of a sequence, and the cold and hot. So cold day, hot day. See, and the arrows going out of from one state to another, or from the state to itself, are the transition probabilities. So remember, we talked about two types of parameters: transition probabilities, emission probabilities. So transition probability is the probability of going from one hot day to another hot day, for example. In this case, it's 60%. So it's indicated here on the graph. And the two tables here refer to the emission probabilities. And of course, only the non-pseudo states will have emission probabilities, right? So because the start state and the end states are just pseudo states, symbols indicating start of a sequence, end of a sequence. But the non-pseudo states, the cold and hot, will correspond to will have emission probabilities. So what's the probability of Jason eating 1 ice cream given that it was a cold day? It's 0.5. So these are just numbers we will come up with just to work throughout the problem. So for each state, you will see 3 emission probabilities, right? Because we said that we have 3 here. We have 3 observations: 1, 2, 3, or 3, not 3 types of observations. So for each state, there will be 3 emission probabilities: 1 given cold, 2 given cold, 3 given cold, and the same for hot. Now, again, what we want to learn here is how to maximize the probability of, to find the S, the hidden state sequence that maximizes the probability of S given O. So we want to find the the hidden state sequence of hot, cold, hot, cold, cold, hot, etc. that maximizes the P of S given O, the observations, the number of ice creams that Jason ate in his throughout the summer of 27. Was it 2007? So what we want to find then, actually, sorry, for some reason I think I copied I changed the title here, so it's a bit misleading. So the title should have been manipulating the definition. So we should change. We want to change the definition that we gave in the beginning. If you remember, the definition of how to compute the joint probability of a state sequence and an observation sequence, and we said it's the multiplication of the transition probabilities and the emission probabilities. But I also said that it's rarely the case that we have both the hidden state sequence and the observation sequence. And as you can see, we don't have it here. And what we are interested in knowing is the probability of S given O, right? And this could be written as the joint probability of S and O divided by the probability of O. This is per the definition of joint probability. This is how we of conditional probability. And again, our problem is to find the state sequence S hat here that maximizes the probability of S given O. So this could be written as the argmax S that maximizes this term here. And argmax is basically an operator that goes through all possible sequences and computes this value here and returns the S, the state sequence that maximizes the value of the conditional probability. And since we are interested in the S, we want to know the S, the state sequence. That's our main interest, not the probability itself, but which state sequence that gives us the highest probability. And we see that throughout the search and plugging in the different S's here, P of O is not changing. It's the same. So for any S, P of O is constant really. So throughout the search, we are dividing by the same number all the time, right? So we can drop P of O because the relative order will be the same. So the values will be different, but the relative order will be the same. And again, what we were interested in is finding this state sequence that maximizes the conditional probability, and we can find that. So it turns out we can just find that by maximizing the joint probability. You see what happened here? So this is then our sort of definition of or our way from going from conditional probability to joint probability. So again, so the task is we want to find the most likely state sequence S, giving an observation sequence O and an HMM. So this is the hidden Markov model that I just introduced with the graph. So these are the values, the transition probabilities, and the emission probabilities. And normally in cases like in hidden Markov model and other problems, the problem of finding the hidden state sequence is typically called decoding. So decoding refers to finding the hidden state sequence. So how do we do this? How do we find the sequence that maximizes the probabilities, the joint probability of O and S? So let's say that our observation sequence, just for simplicity, consists of 3 days. The summer was very short and only 3 days were kept in Jason's diary, so 3, 1, 3. So for each observation, we said that there could be 2 hidden states, 2 corresponding hidden states, right? So either hot or cold. So we can just write out all possible sequences. And how many of these do we have? So we have 3 observations, and per each observation there are 2 states. 8, exactly. So 2 to the power of 3. So we can just write out these different sequences, and there are 8 of them, and compute their probabilities and pick up the one that has the highest probability, and this would be the hidden state sequence that correspond to our observation sequence. Do you think this is a good solution? I mean, in general, the good method to actually decode to find the most likely sequence.
Wouldn't there be a problem if there's a strong prior? So say a hot day is way more likely than a cold day, anyways.
If that's not a it's not a problem, right? It's just it should be encoded in our probabilities here. So if a hot day is more likely than a cold day, then it would be so the transition from the start symbol to the first element in our hidden sequence, in this case, if it's a hot day, would be more likely. So this is a way to encode it. So the transitions here from, where was it? So as you can see, since it's summer, so this is the prior in a sense encoded.
Right, but if you're selecting sequences, don't you risk that it's for each step it always chooses sort of the locally most likely?
Yeah, yeah. But since we are enumerating all possible sequences, we're not selecting, right? So we're just writing out all possible sequences and then computing their probabilities. But this is exactly the problem that I wanted to refer to, is that to enumerate all possible sequences, it's not something you can just say, right? So here we have a toy example. We have just two states and three elements in the observation sequence. But if you have an observation sequence of length 8 and a 45 states, you cannot just enumerate all possible sequences and count their probabilities. So we need to find a way to actually solve this problem. So brute force, write out all possible combinations of sequences and then compute probabilities will not work. So only, yeah, as I said, only two states and a short observation sequence might be doable, but once we work towards more realistic setups, as you will do in the obligatory assignment, you will see it's not possible to do this. So so to make this more formal, for n observations and L states, you will have an L to the power of n sequences. So the growth is exponential in terms of the length of the observation sequence. So in a tree bank part switch tagging problem, you will have 45 to the power of 8, for example, of your sequence is 8. So you can compute that. So it's immediately clear that this is not doable as in to enumerate the problem or all possible sequences. But we can see immediately that there is also an interesting property about these sequences, if you look at them again, is that they share some prefixes. So the first two sequences here start with HH, right? And the second two ones start with HC. So they share some prefixes, some sub or parts of the sequences, which means that these partial calculations, so if we have done this calculation in the beginning for the first sequence, we can just reuse it in the second sequence. And this way, or this property of the problem calls for a dynamic programming algorithm. So you can solve such problems with dynamic programming. So dynamic programming algorithms, you probably have seen it already in other courses, will typically divide the problem into sub-problems, record intermediate solutions to these sub-problems, and then reuse them to make up the final solution. And of course, our problem should be, or typically should be described recursively then, in order to use dynamic programming. There are many examples of dynamic programming algorithms: minimum edit distance, longest common subsequence, etc. And Viterbi algorithm is one of them. And we'll use Viterbi algorithm to decode or to find the most likely hidden state sequence. So again, if you remember, our problem is to maximize S given O. So here we have written out the sequence S. So from S1 to Sn, given O1 to On. Again, it's a multiplication of the transition and the emission probabilities. And in order to define our problem as a recursive problem, we'll introduce a variable. We'll call it vi of x. Vi refers to Viterbi value. And vi of x means the maximum probability of being in state x at the time point I, given that we have seen the observations from 1 to I. So a time point here refers to, you can think of it as the index within the sequence, or word number 3. So I equals 3, or if we think of the ice cream global warming problem being at a time point, say 2, x could be h or c. And the idea here is to basically find sub solution, or not sub solution, sub problems. So by defining this vi of x, where the value of vi of x, so the maximum probability of being in state x at time point I, is a solution up to this point, in a sense. And to compute this, we will depend on this term here, which is, so I mean, it's a recursive definition. So to compute the value of vi x, we will look up the maximum probability of being in a state k at the time point I minus 1, having seen values from observations from 1 to I minus 1. We look up that value. We assume that we have actually already computed that and stored it. So this is the sort of the intermediate solution, and we multiply it by the emission or the transition probability from a state k to x, and the emission probability of OI given x. So of course we will have to do this sort of for all possible states. So in other words, what we are trying to do here is say that we have solved the problem up to point I minus 1. So at point I minus 1, we know the maximum probability of being in state k up to point I minus 1. And we want now to extend it one step further. We want to do point vi or point I. So we want to compute vi of x. So what we do is we go through all the possible ways to transition from I minus 1 to I, and we compute that. We compute the probability, or the maximum. I think the maximum is very important here to emphasize. The maximum probability of being at state x at the time point I by relying on the optimal solution that we have, or not the optimal, the maximum value that we have already found. We'll go through an example. It's a bit complex to explain without looking at the graph. So I think once you look at the graph, you'll understand it. But just remember that there are 3 parts here in the way we compute vi of x. Vi minus 1 of k, k being any possible state, so goes from 1 to L. So L in the ice cream example is just 2, hot or cold, and we have the transition probability and the emission probability. Now, when we reach the end state, the pseudo state, what this algorithm or this computation here gives us is a probability, a value. But if you remember, as I said, we are interested in the sequence itself that maximizes P of S given O. We want to know the sequence. We want to know the path that we followed in order to reach this maximum value. And in order to do this, we will have to keep back pointers. We will have to record how we move from one state to another to achieve this maximum value of Vi of x, so that once we are done with the algorithm and we can backtrace the solution. So let's look at an example to actually sort of make sense of everything I just said. So this is again our problem, right? So we have our observation sequence 313. So the number of ice creams, JSON 8. This is time point 1, so O1. So we'll refer to it time point 1, time point 3, 2, and 3. And we will, and this whole thing is called trellis. You can think of it's called trellis in dynamic programming. You can think of it as a matrix where you have an observation and the possible states, hidden states for each observation. So for 3 it could be cold or hot, for 1 it could be cold or hot, and for 3 it could be cold or hot. And you have the start symbol and the end symbol. And we will fill out this trellis from left to right. So we'll process it step by step. So what this means is we'll start now navigating this trellis, and we'll see so that for the first observation and the first possible hidden state, this is a trivial case. So there is only one way to get from the start symbol to this hidden state, right? So this is the maximum value that you can achieve here can be found in one way only, because there is only one way, which is basically counting the transition multiplying the transition probability from start symbol to a hot day, and the emission probability of 3 given a hot day. So this is pretty basic. That's there is still no maximization here done, because there is only one way of getting from a start symbol to a hot state. And so, but we still record the V value. So now V1 of H is 32, which is just the multiplication of 8 by 4, or 0.8 by 0.4, of course. And we keep a back pointer. So these dotted lines will be our back pointers. And again, here, this is a trivial case. There is only one way to go back. So it's this back pointer going to the start state. And the same for the cold state. So V1 of C, so the maximum probability of being in a state C at the time point 1 is basically just the multiplication of the transition and the emission probability, because we just started the sequence. But now once we start looking at the next time point in our sequence, we'll have choices. So we could come to this to H here either from the previous H or from the cold state. So now we have two choices, and we have to find the maximum probability of being in state H at the time point 02 in this case, given that we have already seen this, given that we have already seen observation 1. So normally, again, the basic components are the transition probability and the emission probability for each of these cases. But now we will add the Viterbi value. So V2 of H is the maximum of the following two options. One is V1 of H times the transition probability from H to H and the emission probability of 1 given H. And the other one is V1 of C times the transition probability from C to H and the emission probability of 1 given H. Do you see that? So, and what we want to find is the maximum of these two. So the maximum of being at state H, given that we have been at state H also, or being at state H given that we have been at a state C. And it turns out that if we multiply 0.32 by 0.12, so 0.12 is coming from here. So 0.6 by 0.2, so we just write it immediately as 0.12. And V1 of C is 0.02, and also the result of this is 0.06. And the maximum is the first one, so the higher value, so we keep the back pointer here. So up to now, so now we have an intermediate solution. Intermediate solution saying that up to the point of time number 2, where we have just seen 3, 1, this is the solution. And we can now reuse this solution to fill out the rest of the, sorry, this is the solution for H. Yeah, I have to emphasize that. So for each of these possible states. And now we can reuse these different values. So now we have stored V2 of C. Now we have the maximum probability of being at in a state C given at time point 2, given that we have seen the first part, and we have a similar value for H. And we can use these two values to continue building up the solution. So we basically repeat the same thing now, but instead of looking at V1, now we're looking at V2 and V3. And for each state, we do the same. So we record that, we keep, we record the maximum value, we keep a back pointer to where we could get to H to get the maximum probability. And the same here, so we had to go from C to C in order to get a maximum probability of being in state C at time point 03. And finally, we reach the end state, and here there will be only one option. So we have to choose between either going from H or going from C. So we do the same multiplications again, and we find that the highest probability here is to actually, or the highest probability of being in state or in the end state here is to come from H. And now, so what we can do is basically backtrace all of these pointers until the beginning, and we get our sequence. So H, and then we know that we had, in order to be to get the maximum probability at time point 3 for a state H, we had to come from another H, and also from another H, and that's our sequence. And back pointers will be sort of an implementation, then you will implement them as a matrix or something like that. So does it make sense? It's a bit it might be a bit difficult to grasp, but it's very important to actually read the book here. It's because the book presented it in a different way, so you might find the book more intuitive and understanding. And the book will actually use the reverse order of what we are doing here. So now, after this, I'm going to present the forward algorithm. The book starts with the forward algorithm and then moves to the Viterbi algorithm. I did the opposite. So now you have at least two ways of sort of thinking about it. Yeah. The last, sorry? Yeah. Here. The emission probability, so to here it's S to H. There is no emission probability from S to H. So the emission probability is only to the observation, right? So, but there is a transition probability. So you can have a transition from a non-pseudo state to a pseudo state, which is in this case the end sequence. But the pseudo states are not emitting anything because they are artificial states we introduced to distinguish between the beginning and the end of the sequence, or not just to distinguish, but also to know which states are more likely to be in the start position of the sequence. And if you think of that in terms of words, that is even more important. Yeah. We will look, yeah. We'll just now, immediately after this, we'll look at the complexity of this algorithm. We'll see how heavy it is. Yeah. Yeah. So, what is? Is the same. In this case, but these are just made up numbers. It's of course more likely maybe to actually end with a cold day, or but yeah. So for example, if the transition is so transition probability from H to an end of sequence is 0, then yeah, I mean, or very low compared to cold. But I mean, you can see that more clearly in part of speech tags. So a verb, how likely will you end up, or a verb, and maybe a determiner. So it's very unlikely that you will end up you will finish your sentence with a determiner like a or the, right? So you'll need something after that, and there the transition probability from a determiner to end state will be very low, if not zero. Yeah.
If this, shall I say, become really huge, will we have to use the logarithm method, or because if it become really huge, then the multiplication will
Yeah.
be a bit small.
Yeah.
And will we have to use the logarithm?
Yeah, you will. Yeah, it's of course it's a safer method to not, because you're still multiplying uh, probabilities here, and the numbers will be small, and typically some cases will be very small probabilities, and then multiplying them. Yeah, but that's more on like the implement. It doesn't matter, because from a for conceptual point of view, it's the same, right? But then rather than just multiplying, you are adding and the logarithmic space.
How do we decide whether to choose the logarithm method or
Uh, I don't. It's up to you, really. But I think, yeah, we recommend that you use logarithms rather than just multiplying probabilities. Uh, yeah. So this would be the pseudo code for the algorithm that you're going to implement. So basically, just very quickly, we have two main components or two main matrices. One keeping the Viterbi values, so the values, the V values that we just introduced, and this matrix would have a dimension of n, being the length of the observation sequence, and L plus 1 being the number of states, plus 2, sorry, L plus 2 for the start and end sequence. So you have 45 tags, plus 2 for start of sequence, end of sequence symbols. And you also keep the pointer, back pointer to the sort of to the solution in a matrix of similar dimensions. And this is the first step that I said is the trivial step. So the first loop here is initializing the values, because as I said, there's only one way you can go from a start state to another state, so you can just compute that. But then afterwards, you'll have to do this nested loop, which is basically comparing the different ways of coming from H to H or from C to H, and etc. etc. So this is just a translation of what I said in pseudocode. Now, what we want to look at is sort of the complexity of this algorithm. So you probably already know. So you already know what's a big O notation. So it's a way to describe the worst case order of growth for an algorithm in terms of its input or the size of its for its input. So typically, when we work with big O notation, what matters to us only the largest order. So if you have a quadratic and linear of the same term, you would only care about the quadratic. If we have constant factors, we just ignore them. And also, you can more or less determine the complexity by just looking at the loops within the pseudocode. So this is our pseudocode again. Let's see how many loops we have and see how heavy or expensive this algorithm is. So we have a first loop, this one here, the initialization, right? And it's doing a sort of looping up to L, number of states. And then we have another loop running up to N, which is the size of the input sequence. And we have another L. Now we have a nested loop. So this is a loop by itself. Now we have a loop running up to N and then up to L, nested within this N. And we have another one L here because remember that we are actually maximizing. We're looking for argmax. We're looking for the maximum, which is a search problem also. So that's, even though it's not written as a loop, but the argmax is actually a loop. And then we have, so the result of this is L to the power of 2 or L squared and multiplied by N. So 3 nested loops here. And also again we have here n for the back tracing of the back pointer, so to find the sequence. And since we're talking about big O notation, what matters to us here is the L squared times n. So this is the time complexity of the problem, of the algorithm. And is this an okay complexity, or is it too expensive? Or who asked the question? Your friend here, right? This is the complexity. Is it? Do you think it's so L? So it's quadratic, right? So times n. I would say it's not that bad. But why? Okay. Yeah. And which one of these is the sequence? N, exactly. So that's exactly what's. Let me just finish this idea first. So n is actually the algorithm grows linearly in terms of the input sequence, which we don't have control over. We don't know. It could be, of course, typically it's not that long, but sometimes it might be too long. But what's restricted, what's limited, even though it's quadratic to the size of the tag set, but we already know that the tag set is 45, and that's limited. It's not going to change. So it's not that bad in the sense that what's actually growing here, or we don't have control over, is the length of the input sentence, and it still takes time, of course, to compute it. But we know that there is no arbitrary number of tags that we or hidden states in this case L, but n could be 1,000, and if the growth was the other way around, quadratic to the length of the input sequence, then it would have been more problematic. Yeah, go ahead. Yeah. Exactly. But since this is linear, it's still more acceptable than space. And as the that's why it's not that bad. It's actually good. It will take time, but the thing is, what matters to us here is that we kind of have an intuition of the largest order here, which is the largest order of growth, which is the number of tags, and that is predefined somehow because you train your model on a tag set of 45, and that's it. You can't just predict use another sort of tag set with the same model. You can have a sort of an intuition of how long it will take. So. Any more? No more questions. No, sorry, but I have to run through the next part, which is as I said, we can use the hidden Markov model to actually predict the probability of a sequence of a sentence. So that's the P of O given O. So given an observation sequence, we want to determine the likelihood of this observation sequence according to the HMM. And the HMM consists of transition probabilities, emission probabilities as their parameters. So if you think about this problem, it's basically what is the probability of O given all possible hidden state sequences that could occur with this O, right? So what this accounts to then is the probability of O is the sum of the joint probability of O and S given all possible S's that can be sort of describing this O, that can be a hidden state for it. So we still have to compute this joint probability. We still have to, because this is the sort of how the hidden Markov model is constructed. So but rather than just looking for the state that maximizes for the state sequence that maximizes p of s given o, what we want is just the p of o. So we sum. So basically, if you think about the again the ice cream global warming problem, you can just list out all possible solutions, compute their joint probabilities, and then sum that value to find the probability of the observation sequence 313. So again, this is a problem that cannot be solved in a brute force manner. So by enumerating all possible solutions, that we're going to employ another dynamic programming algorithm called the forward programming, or the forward algorithm, in which it's very similar to Viterbi, but instead of so we're going to be basically reusing the same intermediate solutions, and we have a trellis. This time we'll call it alpha instead of v. So instead of vi, we're computing alpha I, and instead of looking at the max, if you remember how we computed the value of vi of x, instead of this sigma sign, we had a max sign, right? So we wanted to maximize the probability of being in state x at the time point I. Now we just want the probability of being at we want to sum the probabilities rather than just maximizing, rather than choosing one way and having a back pointer. We just want to sum all of these probabilities. So again, in practice, what this means, this is the same trellis, and here in the beginning you won't see the difference again because it's a trivial case. There is only one way of going to state h from the start symbol, but now the difference here, what we want to do is to sum the probabilities of being at the state h, having been at the state h or at the state c. Of course, that will be multiplied by the transition and the emission probabilities. So we replace the max operator, the maximizer, by a addition or sum operator, and we do that for all possible sort of transitions. And once we arrive here, we will have a final value for the probability of an observation sequence. So if that's a sentence, so we'll have a final probability value for this sentence. How likely is this sentence to be said? That has been counted based or calculated based on the all the different state sequences that can be generated in this setup. I know that I ran through that very quickly, but we can look at this again in next week if you still have problems with that. It's just very also very quick remark on how we can. So you're going to train part of speech tagging model for the obligatory assignment, and one way to evaluate the model, it's a typical setup that we have described before. So you'll have a training set and you'll have a test set. You train your model on the training set, and then the test set is held out as a separate data set. After training the model, you use it to tag sentences, and then in order to compute, for example, the accuracy of your model, you divide the number of words where you got the correct part of speech tag over the total number of words that you try to whose part of speech tag you try to predict. So this is a word based and this is sort of evaluation, not a sentence based evaluation. This is typically what is used. So even though we are assigning a sequence of tags, some people would sometimes report the accuracy based on the sentences. So how many sequences, full sequences you got right. But here this is a more lenient evaluation measure where you count how many elements within the sequences regardless of whether the full sequence was correct or not, and report that. And you can also look at it from a different perspective, which we refer to as the error rate. So the error rate is simply the 1 minus the accuracy. So if you got 90% of the words correct, this means that you have an error rate of 10%. So uh, part of speech tagging then is, just to summarize very quickly, is a sequence labeling problem. So our goal is to predict a sequence of labels. The hidden Markov model is used to represent problems where we have an observation sequence and a hidden state sequence, where this hidden state sequence has a relation to the observation sequence. In fact, it helps us understand this observation sequence in terms of part of speech tagging, for example, and words. We learn the parameters of an HMM, which again, they are transition probabilities and emission probabilities, using the maximum likelihood estimation, which is very similar to which is exactly the same as what we did last week. We use the Viterbi algorithm to decode, so to find the hidden state. Again, in dynamic programming, decoding or finding a hidden state is referred to as decoding, and that's formally we want to find the S, the hidden state sequence that maximizes the probability of S given O, an observation sequence. And the forward algorithm could be used to compute the likelihood of an observation sequence. And the difference between the forward algorithm and the Viterbi algorithm is the Viterbi algorithm is, first, it's looking for a sequence. We want to find this sequence, so we keep back pointers, and we want to find the sequence with the highest probability. So the intermediate steps are looking at the to maximize Vi of X, whereas the forward algorithm is to compute the probability of an observation sequence, regardless of the hidden state sequence. So we really don't want to keep any back pointers. That's one. And for each step, we have to sum the probabilities rather than maximize. So alpha I is computed by summing the probabilities of the different ways of arriving at a state X at time point I, rather than maximizing in contrast to Viterbi. Yeah, that's it for all today, and see you next week.